What's up everybody, welcome to another video. Hope you're ready to flex those brain muscles. In this video I'm going to talk about infinite limits, just like the one shown here. And these are a little bit tricky for one particular reason that we're just going to jump right into. So let's throw back to the informal definition of a limit. This is what you learn in AP Calculus, Calculus 1, how you think about limits intuitively, which is that if the y values of a function get closer to some real number L, as the x values get closer to a from either side, then the limit as x approaches a of the function exists and equals L. So let's look at this example. What happens as x gets closer to 0 from the left? Well, the y values just keep getting bigger and bigger. And the same happens from the right. So one way we could think about this is, well, do the y values approach a real number? And in this case, they don't, right? Because they just keep getting bigger and bigger. They don't get closer to any particular real number. And so we could say this limit does not exist. And this is actually mathematically correct to say. But this is where the infinite limit idea comes in, because what we could also say is, well, I want to provide more information. I want to describe the way in which the limit doesn't exist, because something particular happens, which is that if we approach 0 from the left or from the right, the y values just keep getting bigger and bigger, right? They just get bigger and bigger without bound. They increase. And so we can write that this way by saying this is an infinite limit. The limit is infinity. And this is also correct, right? So two different things we could say that are both true. Infinite limits are a way of describing how the limit doesn't exist by saying that it's because the y values get increasingly large without bound, or increasingly small toward negative infinity without bound. So just to summarize what we just talked about, when we write this statement here, we are not treating infinity as a number, nor are we saying that the limit exists. Instead, we are describing the way in which the limit doesn't exist. And it's because as the x values get closer to a, the y values increase without bound, right? And you could change this to negative infinity, and you could just say decrease without bound. So that's the notation we use to describe this situation, and this is confirmed by College Board. Here's a scoring rubric from AP Classroom that I found for one of these AP Calculus answers. And so here's a task, 1 point for the correct answer, 2 possible correct answers, negative infinity or does not exist. So College Board is in fact accepting either. And this is also just straight from college textbooks. Like this is a Pearson textbook. We're saying the limit equals infinity, and it's describing exactly what I'm saying here, that we use this notation, but we're not saying the limit exists, nor are we saying that infinity is a real number. Instead, we use this to describe why the limit doesn't exist, and it's because the y values become arbitrarily large and positive, is the language it uses here. So just confirming that the stuff I'm saying isn't nonsense, because teachers have kind of different opinions about infinity, and some teachers can get a little bit weird about it. But this is a common thing that we do in math. We write a limit equals infinity, and it's a way of describing, it describes the way in which the limit doesn't exist. Hopefully that makes sense. So let's jump into a couple examples of looking at graphs here. So let's look at left limit, right limit, and two-sided limit as x approaches 0. So from the left, what happens? As x approaches 0, the y values get smaller and smaller. They decrease without bound. So this we can describe as negative infinity, right? We could also write DNE. That's technically correct because they don't approach a real number. All right, from the right, what happens? Well, they get increasingly small again. Sorry, they decrease without bound is a better way to say it. So we can also write negative infinity here. And just a reminder, or DNE would actually work for either of these, right? Infinite limits do not exist. Finally, what can we say? Well, from the left, we get smaller and smaller. From the right, smaller and smaller forever. So since it's consistent, we can write negative infinity. And again, we could also say or DNE. But the reason we like infinite limits is because we like to provide as much information as possible in math. And so why would I just write DNE when I could provide even more information? Like this, when I read it, gives me a mental picture of what the asymptote looks like. It looks exactly like this, from the left down, from the right down, when I see that. So if we could say that, then why not say it instead of writing DNE even though it's correct? Hopefully that makes some sense. Let's jump into one more example of looking at a graph. So we have another graph as x approaches 0 from the left. What happens? Same situation. The y values get smaller and smaller. They decrease without bounds, so negative infinity. But this time from the right, they get bigger and bigger. They increase without bounds. So we're going to write positive infinity. And this time, what can we describe about what happens from the left or the right? Well, we can't say anything consistent, because from the left, they get smaller. From the right, they get bigger. So the most information we can provide is DNE. Right? Because there's not a consistent thing that happens from the left or from the right. Hopefully that makes sense. And again, D and E would also technically be correct for both of these, but I like to provide as much information as I can. All right, let's look at another example here. So this is a very common type of task you'll see where you're given an actual function, and these can be actually quite tricky. And you're asked to find maybe a left limit, right limit, two-sided limit. And in this case, I'm going to tell us use negative infinity or infinity wherever applicable. So provide as much information as you can. Okay, so going back to finding limits algebraically, what would we do if we were out in the wild, right? At a party, someone passes you a note and it says, find the limit of this function as x approaches 2. I would immediately plug 2 in. That's what we always do, direct substitution. And what we get here is 2 over 0, which tells us there's an asymptote, which tells us, I guess there's 4 possibilities, right? Either from the left and from the right, we could have this. They could both increase, and then the limit would be, we could write it as infinity, the two-sided limit. From the left and right, they could both decrease, then we could write it as negative infinity, or they could alternate, like increase, decrease, decrease, increase. So those are the 4 different possibilities. We're trying to figure out which one of those we're dealing with when x is 2. Okay, so we can investigate. One way to do it is to make a table, and I like this way because it works pretty well, pretty consistently. It's kind of hard to make mistakes doing this or conceptual errors. So we can plug stuff in getting closer to 2 from the left. So I can plug in like 1.9. I could plug in 1.99, and then I could go one more, 1.999. I may not even need this, but I'm going to write it out just in case. So what happens when I plug in 1.9? In the numerator, I just get 1.9. In the denominator, I get 1.9 minus 2, which is negative 0.1. Now here's what's cool is you could use a calculator. You could type this in like Desmos or a handheld calculator on your phone or something, but we can figure this out without it too. We multiply the numerator by 10, then we make this a whole number, and we can multiply the denominator by 10 and make that a whole number, right? So essentially we can move both the decimal places of the numerator and the denominator in the same direction the same amount of times, right? Because what we're doing mathematically is multiplying the entire thing by 10 over 10, which moves this decimal place once and this once. So what happens when we do this is we end up with 19 divided by negative 1, which is just negative 19. Okay, hopefully that made sense. We can do the same thing for the next example. What happens when we plug in 1.99? That's exactly what we get in the numerator. And the denominator, 1.99 minus 2, this time is negative 0.01. And so now instead of multiplying the numerator and the denominator by 10, we're multiplying by 100, right? We want to make these whole numbers, move the decimal place twice. Multiplying by 100 gets us 199 over negative 1, which is just negative 199. Okay, so I think I already have a pretty good guess that this is going to be negative infinity, right? It looks like the y values are getting smaller and smaller without bound. And actually, I have an even further conjecture, which is that as I plug this in, I'm just going to add one additional 9 here. But we can go one step further and confirm that. So when I plug this in, I get 1.999 in the numerator. And in the denominator, I get 0.001. Now I'm multiplying the numerator and the denominator by 1,000. 1, 2, 3, 1, 2, 3. And I'm getting exactly what I predicted, negative 1,999. And I can pretty confidently say that the limit as x approaches 2 from the left is negative infinity. The y values are getting smaller. They are decreasing without bound. All right, so we could do the same thing. Find the limit from the right. We could plug in, what would that be? Like 2.1, 2.01, or 2.001. But what I want to push us to think about is how could we do this without making a table? How could we think about conceptually just what happens when I plug in values close to 2 from the right into this function and think about what happens to the y values of the function. This is really hard, so bear with me. Hopefully I can explain this well. How can we think about this? Well, we're going to plug in 2.1, 2.01, 2.001. The numerator is always positive, and it's getting closer to 2, okay? The denominator here is also going to always be positive, 2.1, 2.01, 2.001. I'm subtracting 2 from something bigger than 2. So that's always going to be positive, and it's going to get closer to 0, okay? So I have terms as I get closer to 2 from the right that are all always positive. Numerator and denominator are both positive, so the entire thing's positive. And I have a denominator that's getting closer to 0, which causes exactly what we just saw here, When a denominator gets closer to 0 and a numerator gets closer to a non-zero number, what that means is that the entire thing blows up to either positive or negative infinity, depending on whether the values are positive or negative, right? So in this case, it blew up to negative infinity, but in this case, it's going to blow up to positive infinity because every single output is going to be positive. Hopefully that made sense. We're comparing the numerator with the denominator. If the numerator gets closer to something like 5, 2, -1, -7, while the denominator gets closer to 0, then we can conclude either positive or negative infinity. We just have to investigate what's going on with the terms in terms of their sign. Hopefully that's making some sense. I feel like that's kind of a hard thing to explain. And then here we're just going to write dne. Awesome. All right, let's look at one more example. Unfortunately, I made it even harder. Shout out to Khan Academy for giving me this example. This time we're going to throw in some trig. So we can do the exact same thing. We can make a table. And if all that mumbo jumbo I just said made no sense to you, you can just go back to this method. Make a table, right? It's a little bit weird to think about here because, well, we'll see. I'll show you. So approaching -1 from the left. My students always get confused about approaching negative numbers from the left and right. So from the left, what's to the left of -1 is like -1.1 on the number line. And to the right is -0.9. So I recommend writing this down if you get confused about this stuff. So if we want to approach from the left, we're going to plug in -1.1. We're going to plug in -1.01. And we're going to plug in -1.001. And we're going to see what happens to these y values. So what happens here in the numerator, I always just have x, so -1.1. And the denominator, I have 5 times the sine of what? Let's see if I can add this together. -1.1 plus 1 is just -0.1. So the sine of some negative angle that's really close to 0. Okay. All right, for now I'm going to leave it like this, and I'm going to plug in -1.01. So let's plug that in, -1.01. And the denominator, I have 5 times the sine of negative, let's see, what is this? 1.01 plus 1. So now it's just -0.01. All right, hopefully we're seeing the pattern. This time in the numerator, I'm going to have exactly what I plugged in, and the denominator, right, my decimal is going to shift one more time. So I'm going to have 5 times the sine of -0.001. All right, so if you have a calculator, you can actually find these values and calculate them out. Okay, and once you do that, it should be clear what's happening here. If you don't have a calculator, here's how we can think about it. We can think about the sine of this angle, and what's happening to this angle across each of these terms is it's always negative and it's getting closer to 0. So if we think about angles, we can take the sine of, when they are negative, they're down here, okay, and negative and close to 0. And as they get closer and closer to 0, what happens to the sine value? Remember, sine is the height. So as these angles are getting closer to 0 for the negative direction, the sine is also getting closer to 0, but also from the negative direction, right? The sine of all these angles down here is negative. So all these terms is negative, 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 and they're getting closer to 0, which means the entire denominator is getting closer to 5 times 0, which is 0, while the numerator is getting closer to a non-zero number. And remember what I said about that? That means that either infinity or negative infinity. So let's investigate further whether this is infinity or negative infinity. And really, to do that, we just have to think about, is this entire thing in each case positive or negative? And I think I already said that, but let me restate it. The numerator is negative. The sine of this negative angle is always negative. We have a negative over a negative. This entire thing is positive. Same exact thing happens here. Okay, entire thing's positive. Entire thing's positive. So that means that as we approach -1 from the left, the y values go like this, get bigger and bigger, increase without bound, approach infinity. All right, now what happens from the right? Let's try to think about this without making a table. As I approach from the right, the numerator is still going to be negative, okay, because now we're plugging in -0.9, -0.99, -0.999, right? Numerator is negative in all of those. What's happening to this angle in here inside the sine? That's still getting closer to 0. In fact, we're going to end up switching the sign of all these. When we approach from the right, it's going to be positive 0.1, positive 0.001. So we're doing a similar thing, but we're approaching 0 from above. And so now this time what's happening is that the sine values are getting closer to 0, but they are always positive. So we've confirmed that it's an infinite limit by saying the denominators are approaching 0 and the numerators are approaching a non-zero number, confirming it's an infinite limit. And now we've also confirmed that it's approaching negative infinity. How? Because the numerator is always negative, right? Negative 0.9, negative 0.99. And the denominator is always positive. We're taking the sine of a positive angle, really close to 0, that's in the first quadrant, and then multiplying it by a positive number. So we can just write negative infinity because we have a negative in the numerator and a positive in the denominator as we're making our table here. So again, if that's not making sense, me just explaining it, remake the table. If this didn't make sense at all, maybe just use a calculator, plug in the values, observe what they're doing, find out kind of the expectations of your instructor. But I would hope that my students taking AP Calculus would eventually get to a point where they could think about examples like this one, and maybe even examples like this one that are a little tougher, without fully making a table and just thinking about what is happening as x approaches some number from the left or right. So finally we got D and E. Since these are not consistent, that's the best we can do here. And that's going to be all for this video. This was kind of a hard one to do. Infinite limits are one of those things where when we're looking at graphs, right, the examples started so easy and then eventually they got pretty crazy pretty fast. But I think these types of examples are really important to think about. And if you want to do more of them, hop on Khan Academy. That's where I got this one from. So hopefully this video helped. Like, subscribe, comment with any questions, do all that stuff. And most importantly, keep flexing those brain muscles, and I'll see you all in the next video.